Okay. So let's see. So let me remind you all what we were doing last time. Let me remind myself as well. We talked about this last time. If Kate, the element with minimal polynomial f of x separable, okay. If and only if greatest common divisor of the polynomial f with its first derivative is 1, which I mean, I love this theorem because, I always think of derivatives as something that, comes out of calculus, which is of course true, right? It's this limit and all this kind of business, but actually the formal derivative plays an interesting role here. So we proved this last time, and I think I promised you this one. Outbreak extension. And the characteristic of K is 0, which of course means it's equivalent to the same characteristic of F is 0. Then I've been sort of saying this is folklore throughout the course, well, not throughout the course, but throughout the last little bit. For example, I think I said at one point that an extension is Galois if it's normal and separable. I mentioned that earlier after we defined normality, and then I kept saying, well, this is nothing you ever have to worry about if you're in characteristic 0, because everything's separable. Well, now let's put our money where our mouth is here. And this proof actually, I think, will shed some light on, so if you pay attention to this proof, it'll shed some light on some stuff to come. It suffices to show in characteristic zero, every irreducible polynomial is separable. And of course, the adjective irreducible is important, right? Because of course you can have the polynomial x squared, which is certainly not separable because it's x minus 0 quantity squared, right? But it's also not irreducible, right? So let's suppose, to this end, let's suppose f of x minus a become g of x so in other words, I'm assuming that A is actually a root. Maybe I can extract it some extension field F. Notice that assume this is 0. M of x minus a, the m minus 1 g of x plus x minus a m prime of x. Right. Now, I claim that this is not 0. How can I claim that? Well, so what do we know about? So let's say f of x is minimal polynomial. Right. I don't care what characteristic I'm in. When I take the derivative polynomial, it drops the degree. Right? Everybody agree with that? So, and of course, for some polynomials and characteristic fit, it can drop the degree by a lot, but the degree's got to drop by at least. Agree? And so, if this is, well, I guess I should say it. Right. This can't be 0 because then it wouldn't be the minimal polynomial for A. Now, in K of X, let D so let D be the greatest common divisor, and of course, we have this previous limit that we're working off of here. Notice that D of A is equal to 0 if m is greater than 1. So in particular, m is at least 2. And so note that about the minimality, notice that D of X divides F. D of A is 0, then this contradicts minimality. So m must be 1, and so f of x. So that's what we want to show. We want to show that if you have an irreducible polynomial, you can have a multiple root. Now, let me, anybody, well, let me give you an example. And polynomial x to the p minus 1. Well, we'll call this f of x. What's f prime of x? Well, see, this is an example of a drastic degree drop because this is px to p minus 1. But of course, we're in characteristic b, so this is 0. Right? So if you look at the greatest common divisor of this and its first derivative, the greatest common divisor is actually the function itself, or the original polynomial itself. And notice that, probably not surprising, this is x minus 1 to the p power. And so this polynomial is, in fact, a separable polynomial, or it's actually not a separable polynomial. So let me kind of build on this definition. Okay, can that be extensions? An element U and F is purely inseparable. If it's minimal polynomial, then kx is a form minus u to m. So we say that an element is purely inseparable if you look at its minimal polynomial. If so, you have this minimal polynomial here, of which is an irreducible polynomial kx, and when you pull it up to fx, where it's got the root u, it's a linear x minus u to the n power. The extension is purely inseparable with every element and let me point out, just for the sake of making sure that we're all on the same page, this includes the elements of K, because if you're in K, minimal polynomial for an element already in the base field is x minus K, which of course is of this form, basically with n equals 1. So actually elements that are in the base field of this extension are both separable and purely inseparable. Right, in a trivial sense. And it turns out that the notion of purely inseparable is going to be important in the following sense. In a way that I will make more precise pretty soon, if you have an arbitrary extension of fields, you can divide it up into a part that's purely inseparable and a part that's separable, right? So in other words, you can sort of partition's not exactly the right word, but you can sort of break it up into pieces where you've got a part that's purely inseparable, a part that's separable, and a garden variety element's kind of a mixture of things. And like I said, I'll make that a little bit more precise. There. Probably a little bit ambitious to call this a theorem, but U and F is both separable and purely inseparable over K, and only if U is in K. So K is the intersection of the separable and purely inseparable elements. We'll see what this will help us a little bit in the future. Let me briefly go through this proof because it's not too hard, so I can show off a little bit. So if you have some element U and K, then if U is in K, this implies the minimal polynomial is x minus U. So no multiple roots. Its minimal polynomial doesn't have multiple roots because it's just a linear, and it technically satisfies the definition of purely inseparable element because its minimal polynomial is x minus U to the m, where m is 1. So there you go. And the other direction is pretty easy as well. So this way, suppose U is separable and purely inseparable at the same time, then minimal polynomial of U is x minus U to the m, but if U is separable, then m equals 1 because you're not allowed to have multiple roots. Therefore, minimal polynomial is x minus U and kx. So okay, any questions? Okay, here's a this theorem allows you to clean things up. I had this, I wrote it as a lemma, but I think this deserves theorem more than the previous one. So suppose F and K are fields of K F, and characteristic of K P if is algebraic over K in U to the P to the N. So in well, yeah. Okay, let me make a couple of remarks. So what this says is if you have an extension of fields in characteristic P, if you have an element in F that's algebraic over the base field, then maybe it's not separable, but you can clean it. You can jack that up by an appropriate prime power and sort of flush all the bad stuff out of it so that U to the P to the N is separable. So U itself, the minimal polynomial of U itself may have multiple roots. All right, you may be forced into that minimal polynomial, but if you jack this, there's a high enough P to the N power to where now the minimal polynomial, you've gotten rid of having to have multiple roots, which is kind of cool, right? Let me point out that first of all, you don't need the characteristic of P to be zero. In fact, if the characteristic is zero, then what the theorem says is if U and F is algebraic, then U to the P to the N is separable. Okay, it's also true in characteristic zero, but in fact, there's no such thing. Everything's separable, right? So U is going to be separable, so U to the P to the N is separable, so it's kind of a useless point, but it is probably worth noting that the characteristic P, it just focuses on the important case, but it's really not needed. Okay, so let's go through this. So how can I clean this by taking a big enough power? So degree of U over K is 1, and U is in K, so separable. And this, of course, is U to the 1 power, which is U to the P to the 0, right? So no problem there. Now suppose that F is the minimal polynomial of a non-separable element of degree greater than 1. A non degree greater than 1. And again, this non-separable is not really needed here. It just focuses on the case because if the element U is separable, then any power, it doesn't even have to be a P to the N power, is still separable. Anybody know why that's the case? I mean, F prime of x equals 0, it seems overkill, right? But it's true. So if f of x is sort of why is it the case of the f prime of x must be actually all 0. This is an important part of this. Well, what do we know? So here's what we know. So let me kick you down the road. F of x is the minimal polynomial of u. And not separable. So the question is why do I know that the derivative is identically 0? Well, notice that we know that the GCD of f of x and f prime of x is not 1. Agree? That have common. Now, f of x, let's write f of x this way. Say a x I 0 to say n. And of course, f prime of x is the sum of 1 I equals 1 to n. I could say 0, but of course the first term is canceled out of this. But more importantly, we're assuming it's separable. Let's say n power g of x. And this is, and here we'll say that n is greater than 1 because we're assuming that u is a non-separable element or has multiple root in it anyway. So this is m x minus u to n minus 1 g of x plus x minus u Notice that if u is a multiple root of this, that is, if n is 2 or more, you can also say that u is a root of this as well. Agree? And you can also say that f prime of x is also in kx, right? Because this part of the formula right here, certainly the formal derivative of this gives you, if all the ai's are in k, then I times all the ai's are in k. Everybody okay so far? And what do I know about this? I know that the degree of f prime is less than the degree of f. Let me be careful and precise. Or f prime equals 0. One of those two things has to happen. And the reason I pulled out separate cases, of course, I'm defining the degree of the 0 polynomial was undefined. Right. So either the degree of f prime is strictly less than the degree of f, or f prime must be 0. What's the problem with the degree of f prime being strictly less than f? Good. Because f is the minimal polynomial. Right? And so this can't happen because now this is a smaller degree polynomial in kx, of which u is root. So f prime of x must be 0. That's my only choice, because otherwise I've contradicted the minimality. Now that I've got this, is such that 0, and I do mean the 0 polynomial here. What can you say? Can anybody pick out what must be true about this? So let me take a little aside from my foot and see if we can kind of figure out what's going on. Somebody take this polynomial. Suppose I'm in characteristic 2. What's the derivative of this? In characteristic 2, what we get? Derivative of that is 0. Derivative of that is 1. Derivative of that is 3x squared, but 3 is 1. Derivative, what's derivative of x to the 4? Okay, so that's gone. Derivative, that's going to be 5x to the 4, so it's going to be x to the 4. Derivative of x6. Derivative of x10, 0. So notice the derivative of this wasn't 0. What was the problem? Why wasn't the derivative of this 0? Anybody put it in terms that even a fellow like me, whose parents were obviously cousins, can understand? That's right. That's right. What survived were the odd degrees, right? Okay, so think about this in characteristic P. When you take the derivative of this, in characteristic P, I don't know much, but I know I'm going to have the constant term A1. Agreed? So if I want my derivative to be 0, A1's got to be 0, right? If the characteristic is more than 2, then if the characteristic is more than 2, if it's a non-characteristic, then I'm going to get 2A2x. And that's going to survive unless A2 is 0, right? Can you tell me what form must f of x take on for the derivative to be 0? It must be a form, let's say b0 equals b1 x b2 x p b1 x p. So polynomial, that's the only way that you're going to get a 0 derivative, right? Basically what that says is all your coefficients of all terms of degree 1 or higher must be 0 unless it's a coefficient of a p power. Everybody cool with that? That's an important observation here. So minimal polynomial U is a polynomial in the variable x t. Therefore, U is algebraic less than, strictly less than, the degree of U. So by induction, UP, say to the P to the M power, is separable. For some n. So U to the P to the N plus 1 is separable. And of course, that important observation that the derivative must be identically 0, therefore the polynomial must be in the variable x to the p. That allows us to do that inductive reduction down to the previous case. Okay, any questions? Okay, so let me give you kind of a big theorem here. And that's important because if I have any algebraic element, I can sort of flush it out. I can sort of jack it up to a p to the n power big enough to make it be a separable element. So here we're going to let f be an extension of k. Where p is 0. And K have an extension fields. We have the following conditions are equivalent. Number 1 is purely inseparable over K. Number 2, the irreducible polynomial of any U and F is of the form x to the p to the n minus a in kx. Number 3, if U is an F, if U is an F, and U to the P to the N is in K for some n. The only elements of F that are separable over K are the elements of K. The elements of K. Yeah, I sure do. And F is generated by over K by a set of purely inseparable elements. Let me go through some of this at least. suppose that the irreducible polynomial of any u and f is of this form, right? Then u is in f, its irreducible polynomial is x to the n minus a with a and kx. And k, that is. Then u to the p to the n minus a equals 0. So u to the p to the n equals a and k. So that establishes this. The only elements that are separable are the elements of k. Well, 4, 3 implies 4. So you know that any u and f, there's a big enough prime power of it that blends it down into k. So u and f separable over k. Then we know u to the n so a minimal polynomial so u is the root of that polynomial here, but x to the n minus u to the n is equal to x minus u to the n right? But so if u is separable, then it must be the case that p to the n is equal to 1. Therefore, x minus u is in kx. So u is in k. And the rest of this are kind of this spirit as well. Any questions on it? So that's just a couple of implications, but the proofs are all sort of like this kind of magic here. Let me give you a corollary to this. Again, if the characteristic is P and F is a finite dimensional purely inseparable extension, and finite dimensional purely inseparable extension, then its degree is p to the n. So this is kind of nice because it's very restrictive. This is for the entire extension. So if you have a purely inseparable extension, that's algebraic, well, all I need to really do is say it's finite dimensional, then it has to be of this form, right? Proof. Then suppose I define okay. Okay, sure enough, I've done nothing to further my cause so far. Why does it have to be a power of the prime? Maybe we should go back to induction. So, let you, well, let me point out that if 3 of f over k is 1, end up, because certainly 1 is p to the 0 power, which would satisfy what we've got, right? Everybody cool with that? Suppose not. Then there's ECU in F9K such that, well, that's all I'm saying. Suppose there exists a U that's in F9K. Well, what that means is that since this is purely inseparable, over K, so U, right? Because that's what it means to be purely inseparable. It means that all the elements in there have to be purely inseparable. So if you look at the degree of KU over K, this must be P to the J power, right? Because minimal polynomial of U is a form J minus A in KX. A previous theorem. Agree? So what we have now is the degree of K is the degree of F over KU, KU over K. And this bit is P to the J power. And this bit is what we call M, I guess. So M equals now, from here on out, since we're running out of time, let's see. Verify F is purely inseparable over KU. And end up. Notice that the degree of F over KU is strictly less than M. So notice that if this is 1, then you're done with the original theorem. If it's not 1, then there's another element that's intermediate, and you just keep sawing off smaller and smaller p to the ends until you exhaust them. It's finite. That's a little bit fast and loose, hand wavy there at the end, but let me know if that's not clear, and we can straighten that out later. Any questions out there? Questions? Yeah. All right. Well, you guys enjoy the trip back from spring break, and I'll see you guys on Wednesday.